Hello guys, before talking about the main content of this video, let's record the last video's content briefly. According to the K nearest neighbor's name, we put forward these three questions. As we can see, so far there's no chaining process, right? Yes, KNN is a lazy learning model. That is, to make prediction for the testing data, it's unnecessary to do chaining firstly, but just compute the distance between the testing instance and each chaining instance, and then gather k chaining instances which have relatively nearest distance as its neighbors. Finally, according to the proper weighting strategy, do the prediction for the testing instance. Above all are the implementation of k nearest neighbors. Okay, now let's deal with the three questions we left before. The first, how to compute distance. As attributes can be different types, generally they can be divided into numerical, nominal, or ordinal. For example, as for numerical attributes, it's quite common in our daily life, like height, age, and temperature. And as for nominal attributes, sometimes we always call it discrete attributes or categorical attributes. Taking color as example, green, red, and blue can be its values, and easily to find that they are equal. We cannot sort them, right? And while as for ordinal attributes, the value of them can be sorted. For example, size. It can choose small, medium, and large. And it's obvious to see that small is always smaller than medium, and medium is always smaller than large. So they can be sorted. Here, we assume DAB as the distance between instance A and instance B. For now, let's introduce the distance matrix according to different types of attributes. Firstly, numerical attributes. It's quite common in our daily life, and the matrices are also well known for us. The first one is Euclidean distance, and the next one is Manhattan distance. Here, I just directly show the formula. If you look closer at these two formulas, you could find the general ground, and we can write it down like this. We can surprising to find that when we assign 2 to P, it is Euclidean distance. When P equals to 1, it is just Manhattan distance. Theoretically, it has also a name that is Minkowski distance. Actually, computing distance could be transformed to calculating the similarity between them. In other words, if 2 points are quite similar, the distance between them is much smaller. Therefore, cosine distance could be used, and it is 1 minus cosine similarity. As we know, the range of a cosine is from 0 to 1, so here, normalization is not necessary while using these matrices. Now, to understand it clearly, let's do a quick quiz. Here, we have two instances, dog1 and dog2, and each of them has 3 features, word 1, word 2, and word 3. Then, according to the cosine similarity formula, it can be directly computed like this. And so the distance between dog1 and dog2 equals to 1 minus cosine similarity between them. So the distance is 0.07. In conclusion, as for numerical attributes, there are 4 kinds of distance matrices. Here we go. Since there's no relation among the nominal attributes values, the idea to compute the distance is to do matching directly. The first metric is Hamming distance. This method is to compute the number of differing attributes between two instances, which is quite useful for binary values. For example, here we have to compute the differences between apple and banana, and we record 4 attributes between them: whether it is yellow or not, whether it is red or not, and whether it is sweet or not. Also, whether it is curved or not. Unfortunately, we haven't any finding for whether it is curved or not. So we just assign question mark for curved. As we can see that using Hamming distances, we only concern about the number of differing attributes, right? So here, apple is not yellow but red, while banana is yellow but not red, and both of them are sweet. As for curved, there's no any information about all of them, so it is also matched. That is, the Hamming distance between apple and banana is 2. The next metric is also easy to be implemented. That is simple matching distance. Different from the previous method, it is to compute the number of matching attributes and then use the similar ideas as the cosine distance. Therefore, using this method on the last example, since both of apple and banana are sweet, and the value of whether it is curved or not about apple and banana is unknown, so they are matched. So that is, the simple matching distance is 1 minus 2 divided by 4. That is a half. The third metric is also to match the attribute directly, and it is where we introduced the concept of a set, that is Jacob distance. Firstly, we have to compute the Jacob similarity. It is computed by intersection of two sets divided by their union. And then, as for Jacob distance, it can be computed as 1 minus the Jacob similarity. In the same way, using Jacob distance on the previous example, actually the size of intersection of set apple and set banana is the number of matching attributes, that is 2. And the union of them is 4 plus 4 minus 2. So the Jacob distance is 2 divided by 3. Therefore, in conclusion, as for nominal attributes, we can using these 3 metrics. And apparently, we can see that all of them is just to match the attributes directly. So no, it's not necessary to do normalization. Finally, as for ordinal attributes, since the value of these kind of attributes are ordered, we can use rank to represent distance. Therefore, the ideal of this kind of metric is to transform ordinal metrics attributes to numerical attributes. We call this metric as normalized ranks. For the first step, sort values and return a rank R. The next step is to map the ranks to evenly spaced values between 0 and 1. That is normalization. The third step is to compute the distance function on the numerical features. To be more detailed, let's take an example. Here we have 3 instances and 3 ordinal attributes. Taking the first attribute, safety, as example, we can sort the value of it firstly from weak to strong, not safe, safe, and very safe, and give them the rank from 0 to 2. After that, do normalization. Then we can get this table. Do the same thing for the next 2 attributes, convenient and comfortable. After getting these 3 tables, we can change the original tables where all of the values of attributes are ordinal to these kind of tables. There, all of the values of attributes are numerical. So then we can just recall the metrics to deal with the numerical attributes and use it on this table. Okay, now go ahead. Let's discuss the second question. For fairness, we have to introduce weighting strategies. The first method is quite common, that is majority weight. We always call it equal weights. In other words, we regard all of the neighbors of the testing instances equally. For example, here we have 3 red samples as the neighbor of question mark, and only 2 blue samples. So the majority weight is red. We will say that we predict question mark as red sample. The second method is related to distance. As we know, larger distance means closer relationship. So we can define the weight as 1 divided by the distance. To avoid denominator equals to 0, we have to add epsilon. For example, here we know all of the distances from question mark to its neighbors. And we could set epsilon as 0.01. Then according to the inverse distance formula, we could compute all of the neighbors' weights and then do the summation. As we can see, since the summation of blue is larger than red, so we could say we predict question mark as blue sample. The next metric is quite similar with normalization, and we call it inverse linear distance. The formula of it is look like this. We could also do the simple example using these metrics. Here we also know all of the distances from question mark to all of its neighbors. Firstly, we can get the maximum and minimum distances among them, and then according to the formula, we can attain all of the weights of neighbors. Finally, do the summation of red and blue respectively, since the summation of blue is larger than red. So we predict question mark as blue sample. So far, we have finished to discuss the first 2 questions and only left the last one, how to choose K. Before that, we'd better to look at how K influences the performance of the model. There are 2 pictures which are copied from the blogs. The first one shows the decision boundary when K equals to 1. And obviously that this kind of model has lower performance, where the decision boundary is quite judged, and there's so many single circles, which represent noise. And look at the next picture. Here, K equals to 100, which is a little bit large, and easily to find that the decision boundary is much smoother compared with the last one. And you could imagine that when K is much larger, there will be a danger that all of the instances will be gathered together. Let's say K much closer than n, the number of instances. So this kind of model has also a lower performance. Therefore, we will say that when k is too small or too large, it's not exactly what we want, so we have to choose the best k. Generally, grid searching is a great method to deal with these questions. In Python, grid search CV function will be used. This kind of method is to grid searching the best k with smallest validation error. So you could just remember 4 keywords that represent the properties of a KNN, that is supervised based on distance, lazy learning, and linear model.